one of the big questions was, what are the best qubit modalities? What are the advantages of each technique? What is your perspective from the photonic side?
Yeah, great question. Actually, yeah, I'm gonna just briefly introduce Xanadu in the presentation, but to give you an insight, the photonics has an advantage with scaling because we work with light and you can modularize all of the systems. You don't have to put everything in a fridge. Light has its quantum properties at room temperature. And so when you talk about scaling to thousands of millions of qubits, then this is a place where photonics has a huge advantage. You know, so many technologies from the telecom industry have already been developed to scale, and we can take advantage of that.
And then we will take it off for a great second part of today's session. Thank you, Vardaan. Thank you, Catalina.
Yeah, sure. Thanks, Marlo. So hi, everyone. Welcome to the Software Bootcamp hosted by Xanadu. A little about Catalina, who would be hosting this particular session, is that Catalina comes from electronics background. She did her master's from Los Angeles universities and her engineering diploma from IMT Atlantic in France. And she had a research focus on autonomous systems. But apart from that, she is currently working as a quantum community manager at Xanadu, where she helps build the community around PennyLane, which is a really exciting software. You would learn a lot about that today. Apart from that, she is also working in close collaborations with various professors around the world and helping them include quantum programming in their courses. In the past, Catalina also worked with IBM, where she was an IBM quantum ambassador. And trust me, I could go on and on about what the various achievements Catalina has, but to keep it short, she is probably one of the best persons in the world to talk about quantum machine learning. And hence, she is here today to teach you all about quantum machine learning using PennyLane. So Catalina, the stage is yours. Take it away.
Thank you so much, Vardaan, for the introduction. And I don't know if I'm one of the best people in the world, but I do love talking about this. And I care a lot about the fact that you learn. So this will be a talk where it's a workshop. It's an interactive workshop. I will need everybody super attentive on the screen to really get the most out of today. So let's get going. I will start with a couple of slides just as an introduction, some background. I want all of you to know what we're going to do then in the interactive part of the workshop, but I will be asking questions. And if you don't ask them, I will ask them to you. So the exact things that I did are not super important. The key thing here is, as I heard Olivia mentioning a couple of minutes ago, you don't have to follow an established path. I absolutely didn't. I tried several different things until I found my thing, which is working in quantum computing, working with the community. This is something that I truly enjoy, and I go to work every day excited about what I'm going to do that day. This is one of the paths that you can follow. I did engineering, then transitioned into different areas in technology, in IBM, for instance. And now I work at Xanadu as quantum community manager, getting to meet professors from all around the world, helping them use quantum programming in their courses. So if you're interested in having, quantum programming introduced in your classes, wherever you are in the world, I will leave you a website where you can then contact us. Definitely leave us your email. We want to be able to reach people everywhere in the world. We know that quantum computing has so much potential. It has so much potential for different areas. Today, we will focus on machine learning, on quantum machine learning, but there are so many areas like chemistry. This is one that is particularly important for us, but also different areas in optimization. So we have the need for quantum computing very much in mind. And whenever you are wondering or wanting to, thinking what this is going to be useful for, have this in mind that there are these fields which are key. They are crucial. We're going to focus mostly today on the demo, which is the hands-on, getting the skills. But I will give a little bit of an overview of Xanadu, quantum machine learning, and PennyLane before we dive right in. Let me know if you have any questions on the way. Now, Xanadu is as was mentioned before, a photonic quantum computing company. We are a startup. So we started in 2016, but we now have over 170 employees. And we work using light. So you're going to see here in the picture, there's fiber optics on the left and right-hand side. So this is similar to the fiber that gives internet to maybe your house, your university, your work. This is, I'm going to say, normal fiber optics. But we move that light from the fiber optics into some chips where we modify the light in order to do operations, whatever it is that we want to do with it. In our case, we want to turn that light into something called GKP states. And so these are going to be our qubits. Our qubits are made out of light. Our qubits are, not something that is etched into a silicon chip. Our qubits are really made out of light. And so this is very powerful. This gives us very interesting properties, like scaling. And scaling is so important because we want quantum computers that are useful. Our mission is something that, again, guides us in every decision, everything that we make as a company. We want quantum computers that are useful and available to people everywhere. So I am very, very happy to be here with all of you, helping you get access to the knowledge so that you can then do quantum computing, create new things with it. In order to be able to do something useful, we want the quantum computers to be huge, really big. Again, thousands or millions of qubits. And so this is why we have chosen the photonic approach, because this will get us to that level. Now, we don't only work on hardware or software. We have a full stack. And so the different layers in the stack, right? They start with the design of the computers. We have people working on architecture. We have people working on the nanophotonics design. So we need people from electronics, from physics, mechanical engineers. We need people with a lot of different backgrounds. There is one step here that you don't see, which is the actual fabrication of the chips. We don't do them in-house. We have partners who fabricate them for us. We leverage the ecosystem, and this is also something that I hope you then carry on as you move into the field. Working as a team in the ecosystem, work with other companies is very important. One company may not be able to do everything, so we want different companies to be able to provide the most value. And then from the chips that our partners fabricate, we test them, we make sure they do what we want them to do. We package them into a quantum computer, right? The quantum computer is not only a chip, sometimes it's bulk optics, it's big lenses, or maybe big like this. Lenses or mirrors. And then we package them together into a quantum computer that then people can use. There are different software products that we also have. The main one is PennyLane. It's the one where we're going to focus today. And it's over this that we focus on our applications. So we focus on battery development, simulation of new generations of batteries. This is something that is very important for so many subfields in the world. So this is something that you will hear a lot about from Xanadu, simulation on chemistry and battery development, as well as quantum machine learning. So it's great, for us to be able to talk about quantum machine learning today, because we do fundamental research on quantum machine learning, not focusing on one specific application. We focus on the core. What is quantum machine learning? What is it going to be useful for? These are fundamental questions that we do research on. And one of the main researchers that we have at Xanadu, Maria Schuld, she's probably one of the most well-known researchers in the field. Really, really great person and great inspiration as well. And she leads an amazing team of researchers. Now, just to finish up a little bit on what Xanadu is and our hardware, you're going to see that our roadmap is built off different computers that we have already built. So our X series chips are the quantum computers that we released in 2019. We still have them on the cloud, so you're still going to be able to go to Xanadu Cloud and use our X8 quantum chip. This works differently. So if you're not interested in photonics specifically, this is going to be very hard because they use different gates. It's a very different way of working than, you know, what you will be used to with PennyLane or other, other frameworks. If you are more interested in algorithms, I would focus on using PennyLane. But this is our hardware that we have in the cloud right now. Borealis is our next generation. So Borealis is not one chip. It takes an entire optical table. So it's, let's say, the size of like a dining table. It includes bulk optics. So again, not a single chip. It starts with one laser and in a single fiber optics. So imagine like a single cable. You put all of the different qubits in. They're not exactly qubits. They're Q modes, but they work similarly as qubits. And in the experiment that was published in Nature, which is probably the most important journal, we had 216 qubits or Q modes, which we entangled into a very complicated problem. So Borealis was designed to solve one specific problem called Gaussian boson sampling, which is very hard. And it was designed to beat classical computers, not for something particularly useful. So this particular calculation wasn't useful for a specific application that you may think. It's more about the fact of building something so powerful that it beats all possible quantum computers by a lot. The experiment that was published, it would have taken 9,000 years for a classical computer to do it. Well, for this computer, it took 36 microseconds. And so it's a really, really powerful computer. It was online for free for 1 year. This is also very important. Putting stuff online for people to use requires, a whole different layer of expertise and support and calibration. So we were very happy to be able to provide that for 1 year. And now we have shifted focus to our fault-tolerant modules. So we're looking now further away than the NISQ era. We're looking into putting all of our architecture together. We have developed, and Borealis and our X-series quantum computers were necessary to develop key technologies that we are now building into a fault-tolerant module. This will have a few logical qubits, and this is again in the process of being built. But we have all of our efforts concentrated on this new generation, right? The generation that will be so much more powerful, and that eventually could be built, if you stack all of these modules together, we want to be able to build a data center, a quantum computing data center. And for this, we need to, again, partner with a lot of hardware, software, and application companies. And so you're going to be seeing big names and small names, startups and huge companies. We work together in order to be able to solve these very, very hard problems that we want to solve. Now, we're going to start with quantum machine learning. I hope everybody is very excited. Everybody is very concentrated. And if you do have any questions, this is a moment to ask them. If you have any questions about the hardware, go ahead before we dive right into quantum machine learning. Okay, let's go there. Yes, there is a question.
There are a lot of questions on the Discord, and I would be fielding all the questions to you. One of the questions is, what is the real advantage of photonic qubits over non-photonic ones?
Good question. Also, there are different kinds of photonic qubits. So we don't work with one single photon. This is something that you should know. Different companies that do photonics do it differently. So we work with beams of light, pulses of light. One of the big advantages is that this light works at room temperature. We don't have to put all of this. I mean, Borealis, for instance, it took up an entire optical table, which is, I guess, maybe like 2 meters long by 1 meter long. This is a big setup. You don't have to put all of this into a fridge. You can do almost everything outside. This allows you to use different materials. It is easier to work with if you don't have to always put something in the fridge. This is one advantage. Another advantage is the fact that you can use traditional telecom technologies like fiber optics or silicon nitride chips. These are technologies that are maybe they have advanced over so many years, and we can just leverage all of that advancement. We don't have to build everything from scratch. So then when you want to scale, it's useful. And something that is also very important, our architecture is built for error correction. So it's built into the architecture. Our GKP qubits are integrated together into what is called a cluster state. So you can imagine it like the matrix, like this 3D thing where you encode your error correct, you put your error correcting codes. And so this will allow for error correction. And the fact of having these three things, being able to work mostly on at room temperature, scalability, and modularity, right? Being able to be modular and scalable, as well as error correction being integrated into the design of the quantum computer. These are very, very powerful things that we think are key, they're necessary, and this is why we think our approach has a lot of potential. Now, it's important for everybody to try their own approach, and as Marlu said, sorry, maybe some of them will be more advantageous for some use cases than others, but we really believe that if we want to get to thousands or millions of qubits, the advantages of photonics are going to be dominant. This is our approach. So great question from the person who asked that.
Thank you,
there are
Vardaan.
other questions.
Yeah, there are a lot of questions coming on this call. I'll just quickly choose a couple of them more. There's a question from Mahaya from Iran. She's asking that which type of quantum photonics platform do you use? Is it continuous variables or something of that sort? And also, how does initialization, manipulation, and readout on the platforms are done?
So first you start with a laser, and yes, it's continuous variable. You start with a laser, you squeeze the light, then you pass it through an interferometer, and you generate GKP qubits, GKP states. And so those GKP states, you pass them through a multiplexer because you cannot generate them with 100% probability. You pass them through a multiplexer and then into the cluster state. So this is how we create our qubits and how we put them together into something where we can then apply gates to them. I don't know if this answers the question from the person who asked them.
Great. Yeah. One last question before you move forward. This question is from Brian from US. He asks that, have you made any attempts at networking the photonic hardware? Example with something like QNX hardware?
I didn't get the question. Can you get that again, please?
Have you made any attempts at networking the photonic hardware? For example, with QNX hardware?
I don't know anything about QNX hardware. I'm sorry, I don't work with the hardware, but networking is something that we have worked on, and you need networking in order to put them on the cloud, for instance, right? So the X series chips and Borealis, we did all of the networking necessary to put them on the cloud. And the X series, the X8 chip, is still on the cloud. You can use it from Monday to Friday in Canadian working hours. You can still use it. It's on the cloud. Like we did all of the networking, all of the processing to be able to put it on the cloud. I don't know about the other thing that they mentioned, but maybe if they do have questions, stay until the end. I will share the link where you can ask more questions, and then we can forward them to other people at Xanadu if necessary. So definitely stay tuned until the end, where I will share more information or where to ask these advanced questions.
Sure.
Okay, now let's dive direct into quantum machine learning. First of all, we all know quantum circuits, right? I hope that by now everybody knows quantum circuits. You have some initial state, you have some gates. These gates take some parameters. So the horizontal lines, we call them wires. They are qubits, but we acknowledge that some some technologies, your Q modes, but for the rest of the talk, we're going to talk about qubits. You have your gates. Here we have some Y rotations, and they take an angle, right? In this case, they are parameters. But this could be fixed data that maybe you wouldn't want to change. So you have some initial state, you have some matrices, and you have a measurement. And so everything that happens before the measurement is just linear algebra. And I'm not going to go too deep into the linear algebra, but it is going to be important. So quantum machine learning, QML for short, you're going to see that it's often called QML. It's all about finding patterns in data. And so key elements here, you need data. In order to do quantum machine learning, you need data. And it's sometimes hard to distinguish what is optimization, what is quantum machine learning, what is something else. For quantum machine learning, data is important. It can be a little data or a lot of data, but data is going to be key here. And you're going to be able to find patterns, not by programming something specific, but by running your data through a quantum computer, by having some useful, some very smart algorithms, you can then find the pattern, right? So the classical example is, tell me whether this is a cat or a dog. This is probably an example that is not very well suited for a quantum computer, but it can give you an idea of what does it mean to find a pattern in data, right? In the image that you see on the screen, you're going to see that your circuit has different gates. Some of them you will modify, and then you will perform a measurement, and this measurement will give you an answer, right? It will predict, your quantum computer will predict whether a new entry that it has never seen is dead or alive, cat or dog, or, you know, some other process as well. It doesn't have to be a classification. The example that I'm giving of given a certain image, is the cat dead or alive? This is a classification problem because we're classifying our data into separate categories. But there are a lot of other problems that you can do. An example is also regression. Maybe you want to find a trend. It's not all about finding, is it A or B? Maybe it's about fitting data to a curve, fitting data to a line. This is a regression problem. And this is also something where quantum machine learning can work, right? There are different tasks, but these are some examples that are often looked into. If you like math, and if you don't like math, it's okay. You don't have to hang up yet. But if you do like math, you may recognize some of the items that I have here on the slide. So first, you start by plugging some information into your quantum circuit. You start with an initial state, and then you have a matrix a matrix U, which is called a unitary. So it's just a special matrix U, which takes some parameters some parameters that we're going to call theta. If you think about functions, if you're used to, let's say Python, for instance, imagine this as a function that takes some arguments, right? So this is a matrix, which is parameterized. It takes some parameters, theta. And at the end, you get a different, a modified version, right? So you get a different state. If you write the math, then you can also understand how to find a new version of the parameters, right? So you want to build algorithms where your quantum circuit is not going to be fixed. The parameters that I use in step number 1 are not necessarily going to be the same that I use in step number 2. And so I will have a rule to update or to find the new version of my parameters. And so the new version of my parameters will depend on my current parameters, because I need to know where I stand, and they will be updated by a function that depends on the gradient of something that I decide, which I'm going to call a cost function. So I know I said function a lot, but basically, my circuit is a function. And I can use this function that represents my circuit to build another one, which I will call my cost. This can include some classical processing. This can be a combination of several quantum circuits. This can be something else. But the key here is that this will give me an answer to my problem. My cost function will give me an answer of whether I am trying to maybe minimize, maybe I'm trying to buy something. Maybe my problem is about buying something and minimizing the cost for that, literally the cost. Maybe it's about optimizing resources in some other direction. Maybe it's about reducing the distance between the points that I have and what my circuit is predicting. This is what my cost will represent. And my gradient, what it will do is that it will find where my cost function moves towards. So it will find the direction of maximum change in my function. And so if I look, let's say, at this landscape, let's say this is my cost function, what my gradient will tell me is if I stand here, if I stand on a specific point, what is the direction of maximum change? And so what it will tell me is how I can go downhill, right? The gradient will tell me the direction of the steepest change in my function. And it will allow me, thanks to the algorithm that I made, it will allow me to choose a new version of my parameters, which means it will allow me to stand on a different point and try again and see what our cost means. And so at the end, the math is not super crucial right now. Don't worry. This is just for context for those of you who really like math. But really the key here is that I will not specifically program what to do. Let's say I won't do an if else statements, right? In quantum machine learning, you will not have in general, if this, then that. You will have a more general program where the underlying math will help you find the right answer. And so you have to set up your cost function to answer your question, right? This is an important thing in quantum machine learning. How will I set up my cost function so that it answers the problem that I have? And then when I stand on a certain point, I will know in what direction to move in order to get to a better answer. So modifying my parameters here, fine-tuning them here, step by step, is what machine learning is going to be able to do, quantum machine learning. Of course, in quantum machine learning, there has to be a quantum computer involved, right? Whether it is to optimize or to change the way or to enhance a machine learning program. This is something that happens a lot. You will have a quantum part inside of a machine learning program, and it will become a quantum machine learning algorithm. Something very important, machine learning and quantum machine learning is not deep learning. Deep learning is a sub-part of machine learning, but quantum machine learning is more than that. It's not only deep learning. It's not only neural networks. Quantum machine learning is about finding patterns in data, and it is not only about neural networks or deep learning. It's more than that. There are methods that don't include gradients. So you have options of modifying your parameters without needing gradients. But for the most part, gradients are very, very useful, right? Gradients, which are, again, the direction of maximum change in your function, which will help you find the new versions of your parameters. They will be used a lot, and there are different methods for calculating them. But one question that we usually don't ask ourselves is, how do we calculate this on actual quantum hardware? And hopefully maybe you haven't even asked yourself the question, can I do everything on quantum hardware? Can I do absolutely everything? Maybe not. Hopefully some of you have asked yourself the question. But for quantum gradients, it's something that we're usually not aware of. And it's important to ask ourselves the question. So not everything that happens in a classical computer, you can do in a quantum one. One example is called backpropagation. So for those of you who know a little bit of machine learning, backpropagation does not work on quantum hardware. At least so far. We don't know, maybe in the future we'll find a way to make it work, but backpropagation does not work on quantum hardware. So how do we do this? How do we do machine learning on quantum hardware? We can use other methods. And one method is called the parameter shift rule. So it's the one that you have here in blue. You can use your circuit. You can run your circuit twice. So you run it once with some parameters, and you run it a second time with a modified version of those parameters, the same circuit, but with different parameters. And then you can use this to calculate the gradient of your circuit. So this is one method that does work on quantum hardware. It's called the parameter shift rule. It has actually different variations. So you will be able to use this to do training via gradient descent, for example. You will have some initial parameters. You will get the output of your circuit. You will find the gradient using parameter shift or other methods. And then you can get a new version of your parameters. And within PennyLane, for example, we have what we call gradient recipes. And you will not need to worry about this when you use PennyLane, but it's good for you to know. It's important to know, how do we run something on actual quantum hardware? What can we do? And parameter shift rules are here, very useful. It's a useful tool. It's analytical. It doesn't have a lot of carried errors. It's a rule that is built in for you to use, even if you don't even notice it. But it can be very powerful for something like quantum machine learning. So just a recap, just a quick recap. In quantum algorithms, you won't program something specifically. You will try to find the model underlying your data. You will try to find a pattern. You will use usually something like gradients. And depending on where you're running, you will use, say, backpropagation if you are running on a simulator, or you will use something like the parameter shift rule if you're running on hardware. And these are calculated by PennyLane for you. If you are doing the parameter shift rule, this involves running your circuit twice. So normally you won't need to do that. The software itself will do it for you. So in this case, PennyLane will do it for you. But this is something good to know. How do we run something on quantum hardware? And now that you know all of this, you can learn how to build variational algorithms. So here we go into the more lightweight part. This will become only easier from now on. We went through the hard part. Variational algorithms are, again, all about iterations. You can create an ansatz, which is like your initial guess for your gates. Your output, you will often use an expectation value. This is just an average measurement, you can imagine, over a lot of shots. And you can combine different quantum circuits with all of the different measurements into a cost function. You can use a single one or different ones. And you can then define your training procedure. So how you're going to find a way to reduce that cost. There are other and advanced methods, so it's not all about variational circuits. There are other methods. If you're interested in learning more, kernel methods is something where there's research on, basically they help us map the information into a different space. And so this can be interesting to see how we can, for instance, make a classification if your space is mapped differently. There is still a lot of research going on in this field, but hopefully this can give you maybe an eye-opening into the different options that you have. You can have, kernel methods or different variational algorithms, as well as many others. I'm not going to go into the details about this because I know that we want to go into the workshop. So just to give you a sense, this will all come together into hybrid algorithms, right? You will use classical and quantum together. Quantum on its own is limited. You will need to work together with classical computers in order to make powerful quantum machine learning programs. In order to make rich end-to-end models, you will need to work together with classical and quantum. So in the short term, hopefully we can be able to represent our data differently, to maybe get a different insight on how to answer our complicated problems. And in the long term, in the future, we want to be able to train faster or train better. It's not only about faster. So this is something very important. Quantum machine learning is not about just being faster. Sometimes it's about being more precise, right? Not all quantum machine learning, and for the most part, quantum machine learning at the moment will be slower. It will be slower than classical one. So it's not all about speed. It's about more than that, right? It's not all about speed, and sometimes it can even be slower. But we want to be able to explore maybe hard problems where it's not about how fast, but maybe how precise we go. Let's give some time for questions again. Vardaan, I don't know if we can maybe read out some questions that we have.
Absolutely, and there are a lot of questions. So one question I would like to put up right now is, how do Bayesian machine learning models map to the quantum computing systems? Like, is there an equivalent to something like a Gaussian process model?
So these are like, let's say this is a high level thing. Here we're not talking about how the system is exactly, right? Let's say what is in this blue box, it could be a photonic system working with, Gaussian states. It could be a superconducting qubit system. It could be trapped ions. It could be something else. The gates would change. The gates inside it will change. But the whole idea, the algorithm itself, the variational algorithm, normally would be the same. So the exact technology, you can plug it into the blue box here. It will change, but the algorithm, let's say the higher level algorithm, for the most part will be the same. There may be some limitations, I agree, but it really will mostly be the same.
Another question is about the compatibility of the Xanadu photonic hardware with respect to quantum machine learning models. And the question is, what is the resource capacity of the current hardware? Like, what is the circuit depth? What is the ideal number of gates that could be easily run in order to create a good quantum machine learning model?
Good question. So remember how I said we have different generations of hardware? Borealis, for instance, is no longer accessible, but it was designed for a specific problem, right? The previous generation, which is the X series, it is designed it's a generation from 2019. So, it's a little bit old now, but it's still valuable to learn about photonics. It is small. It has the equivalent of 8 qubits, but it's also limited in the sense that it's made for bipartite graphs. And so you need to have a problem that can be represented as a graph. and then you input it into that particular computer. We have tutorials on how to do this. For instance, we have examples with for chemistry simulations, very small simulations, or there is one really good article about comparing the max click. It's a graph problem comparing the advantages or disadvantages of a photonic quantum computer or our X8 device and one of IBM's computer. Again, this was a few years ago, so I don't remember exactly which one, but you can see some advantages and disadvantages there of how the technology works. I think there were other sub questions in that question, but I already forgot the second half.
Yeah, I think you covered it all. The second question was basically what circuit depth and how many gates are usually run on the current hardware.
I don't remember exactly. So for X8, I think you have SU4. You can have SU4 or SU2. I think SU4 matrices. So it will, yeah. I think I would have to look deeper into that. I will give you the answer. Well, I will show you how to get the answer later. And the number of qubits is 8.
Right. There's another question regarding the cost function, and I believe you would be talking a bit more detail in the rest of the lecture. But a lot of participants are curious, how do you come up with a problem-specific cost function? Like, what are the processes involved in that?
Yeah, good question. There are some examples. So say if you're working with a, let's say if you're working with a chemistry problem, you may want to try a Hamiltonian. You will want to find a ground state. If you're working with data, I will show you an example today of you create, basically you want to compare to a reference. You want to compare to some other information, right? So you will get a, yeah, you will get a number that will be how close you are to your target. In case you have supervised learning, for instance, you can do this. There are other examples. So in reinforcement learning, you will have, you will be able to create a, like a target, like a system of points, where the exact design of the cost function, it's really dependent on the problem. So yeah, basically I will show an example of how we can build one, and then if the question remains, then we can look at it later.
Absolutely, look forward to that. Another question is from Carolina from Venezuela. She asked that, what is a feature map? Could you please talk a bit more about that?
Oh yeah, of course. So let's say you have some data. Here I have my red squares and my blue circles. And I want to separate the circles and the squares by using a single line. Now you can think about it a lot, but really it's very hard to think of one line that will help me separate the squares and the circles, because they're all basically like mixed together in a way that is difficult to separate. So if I use a quantum computer to basically modify the layout of my data, so basically you're let's say creating like a different version of your data in a different in a different feature space. How do I explain this? This is like a different layout, right? It's like you have some information here, and you are getting, imagine like a shadow, or you're getting a projection, right? You're kind of moving your data from one way of looking at it. Imagine you're looking at your data in a flat space, and now you're mapping it into different layers, right? So you're kind of expanding the information in your data, right? So that you can then pass a line through it. This is basically what it means. It's you no longer are looking at your data in a very flat way. You're looking at your data with a higher dimensionality, and this can allow you to sometimes find boundaries that would be impossible to find in your original data space. I hope this gives an image for the person asking the question of what it means to map that data into a different feature space or a different dimensionality.
Excellent. And there are a couple of questions more, but I would suggest you could start with the bootcamp because that might take a lot of time. And I will stop in between if there are more questions.
Yeah, perfect. Perfect. So in PennyLane, we're going to do a code example, but PennyLane is more than just code, right? So definitely go to check PennyLane.ai for more code examples, to learn, to meet with people. It's really a community. It's not only code, it's a community. We've talked about all of the different items that we have here. PennyLane is built with open source in our minds. Like it's crucial for us to be open, to be easy. And I know that today seems hard, but believe me, PennyLane is much easier than that. I gave you the hard talk. I gave you the advanced one. And you are going to be able to try out different hardware by using PennyLane, hardware and software, right? So today we're going to focus on simulators because we don't want to wait on the queue for a long time. And later on, hopefully you will be able to use different software as well. Maybe some of them you're already used to. So if you like already using PyTorch, TensorFlow, JAX, NumPy, you will be able to work together with PennyLane. Today we're going to use, we can use different simulators. So we're going to use lightning.qubit. It's built on C++, but you don't have to worry about this. You can use it with Python. It is a fast simulator. And if you do have access to GPUs, we have a device that works with NVIDIA GPUs. So you can try that out after today. And if you want to work with noise, then we also have simulators for that. Today, we're going to use a Q node. It's going to be something that is basic and a signature of PennyLane. We use Q nodes to encompass everything that is quantum. You have your data and your parameters. Your data is non-trainable. You don't find gradients over your data. Your parameters are trainable. And then you output or your return of your function. This is going to be a Python function. Your return value is going to be your measurement. And so this will be a classical output. And today we're not going to try it, but you can, if you want, try to integrate it with, say, PyTorch, for example, to embed your data, and for your measurement to embed it back into, say, a PyTorch neural network. And if you want later on, you can try even templates, which can allow you to create your ansatz in an easier way. So we have some tools to make it easier for you to do quantum machine learning. This is also why we're very, very known for this. A lot of people, you want flexibility and ease in order to plug your data into your circuit and then, do a lot of things with your circuit. This is a little bit more advanced concepts. Maybe I'll go back to this at the end if we have some time, but we probably won't. So just to mention, we have some advanced concepts like circuit cutting, where you can split a quantum circuit into parts so that you can run it in smaller hardware or simulators. So if you're interested in this, again, we have a demo, or we can answer some questions at the end. So now let's dive into the demo. If you have not installed PennyLane yet, that's okay. Open a Google Colab and do !pip install PennyLane. Will take a couple of seconds. And you should be seeing my screen right now. Yeah, I think you're seeing my screen. I want to wait for everybody to be ready. So I don't know if you can, maybe Vardaan, if you can tell me if if somebody is not ready, if they're saying it in the comments. I wanna start when everybody is ready. So if you are using, if you're locally using PennyLane, you need to just open a Jupyter notebook. If you are using Google Colab, for example, you can do pip install PennyLane like this, and then this will install it in a couple of seconds. So I will wait for Dan to let me know if they write something in the chat, if everybody is ready to start.
Yes, first off, your screen is perfectly visible, so that is great. And a couple of participants are just following it along, so give them a couple of minutes, I would say, to create the Jupyter notebooks and get started with it.
Okay,
Yeah,
perfect.
so let's wait for a couple of minutes and then we'll start.
Awesome. In the meantime, we can answer some questions.
Absolutely. So yeah, another question which was asked on the Discord a while back was about quantum machine learning in general. Has there been a quantum advantage seen yet, especially for quantum machine learning?
Ooh, great question. I will recommend one blog post by Maria Scholl, where she talks about why are we all trying to sell quantum machine learning, basically, right? Why do we want to work really hard, but the question of quantum advantage has to be compared to, it has to be properly asked. Why are we using, for instance, these classical data sets that maybe don't make sense for the problems that we are trying to solve, right? So there are problems. There's like this, quantum advantage in learning from experiments. It's a very good paper where you can see that quantum machine learning indeed performs better than the classical version. It's a toy problem, right? It's not particularly useful, but it is a case when quantum machine learning proved an advantage. In some other cases, you will see that a lot of people use simulators, which is very good. It's very useful to be able to develop new algorithms. And you will hear people talking about quantum inspired, right? Quantum inspired algorithms. That is valid, and it will help also the classical machine learning world advance. But I personally haven't seen a business application where there is a clear advantage. So hopefully there will be one, but we really need to compare, make sure that we have this critical thinking of, are we comparing the right thing, right? Are we asking the right question? So her blog goes a lot into detail about this question. Definitely check it out. I will show you where to find the blog later on if you want to look for it. And it really delves into the question of, yes, you might find this little example where there is an advantage, but does this prove a general one? Or what question are we trying to ask?
Yeah, absolutely. Just share the link afterwards with me or the WOMANIUM team, and we'll share it further with all the participants. Just a quick doubt about the installation of the library, the PennyLane. Could you just repeat the steps involved? And another question is, do they need to start with a new Jupyter notebook, or is there something else which they need to load?
Just a new Jupyter notebook. Any Jupyter notebook works. If you are on Google Colab, for example, if you're on Google Colab, you will need pip install PennyLane, like this with the exclamation mark. If you're not on Google Colab, if you're on your, let's say, if you're locally on your terminal or your command line, you will need pip install PennyLane. And if you don't have Jupyter installed, you will need to install Jupyter. If you don't have it installed locally, I would recommend try Google Colab. It's quick. Normally, it should take almost no time to get started.
And yes, I guess we are ready to start. I've received a lot of ready messages on the Discord. So yeah, please go ahead, Kathleen.
Perfect. Okay, so hopefully by now you know what your favorite library is. So we're going to import PennyLane as QML. So as you can imagine, QML stands for Quantum Machine Learning. It doesn't mean that PennyLane is only for quantum machine learning, but of course we're very good at it. So we keep this, import PennyLane as QML. And from PennyLane, we are going to import NumPy as NP. So you hit Shift Enter, and this runs the cell. So it will import PennyLane into your program. And now every time that we want to use PennyLane, we will simply use QML. NumPy is a numerics library, so it's useful for some numerical calculations and stuff. And this is our own PennyLane version of it. It has like some additional, it's almost the same, but it has some additional things. Now, a quantum computer, we're going to run on a simulator, so it's going to run on a classical computer. We're going to call it dev, and we're going to use QML.device, open parenthesis, and comma, lightning.qubits. And I'm going to add 2 wires or 2 qubits, right? So you will notice that in PennyLane, we call the qubits wires, basically because if you draw a circuit, they look like wires, right? So you can imagine those qubits are actually wires. And we're going to do Shift Enter. It's here that we could use a different simulator, and we're going to try one later. Now we're going to create a key node. And I mentioned that this is something that is key in PennyLane. We're going to do @qml.qnode, open parenthesis, dev. This will basically say whatever I add just below this line, run it on this particular device called dev. And so this allows us to then define a normal Python function. I'm going to define def circuit, open parenthesis, I'm going to leave them open. And now I can add my gates. And basically this function will represent my quantum circuit. I could call it whatever I want. The name is not that important. What is really important is that I have this line right above. So now I can start adding my gates. So, I know that you're asking the questions on Discord, but maybe you can start saying, what gates do you need to create 2 entangled qubits? So hopefully somebody here will have an idea. What do you need to create 2 entangled qubits? We're going to need a Hadamard and a CNOT. So these 2 gates, we're going to add them as QML.Hadamard, open parenthesis, wires equals 0, and QML.CNOT, open parenthesis, wires equals, open brackets, 0,1. Okay. So basically what this means is in the first wire, which is wire number 0, there is 0 index. So we have 2 wires or 2 qubits. From these 2 qubits, in the first one, which is qubit number 0, we're going to add a Hadamard. And in the, first and second one, the qubit number 0 is going to be our control, and qubit number 1 is going to be our target. And now we can add a return value for our Python function. We are going to perform a measurement. So let's say we're going to return the probabilities. Let's say QML.probs, open parenthesis. We do Shift Enter. And now we're going to draw the circuit. I already have it drawn. So this is I guess, a spoiler for you. This is how the circuit will look. But now we are going to draw it. So we are going to write QML.draw_MPL. And we are going to say, I'm going to draw the circuit. So I'm going to add the name of my circuit. I'm going to add some empty parentheses. So why do I add these? I add these because my circuit does not take any arguments. It does not take any parameters, any data, anything here. So this will be empty. So now I will do Shift Enter again. And as you can see, surprise, it did draw the circuit with 2 entangled qubits. And now what answer will I get if I run my circuit? So this is drawing my circuit, but not running my circuit. If I want to get the answer, what are these probabilities? What do you think I will get? If I have 2 entangled qubits, well, let's run circuits, open and close parentheses, Shift Enter, and I get 50% probability for 0, 0, and 50% probability for 1, 1. So this is probably what you expected. If you have followed so far, you have just created your first quantum circuit with PennyLane. And I know this will be different to what you, maybe some other libraries work differently, but as you use this will be so powerful because you can use the things that you already know from Python, functions, etc., to build your circuits in the way that you like them. So I will stay here for a minute for those of you who maybe joined a minute late to get up to speed with what we did. We imported our favorite library, PennyLane. We created one device, which is in this case a PennyLane simulator called Lightning Qubit. We created a Q node with @qml.qnode. So our circuit is a Q node. And when you keep using PennyLane, if you get maybe an error message in the future saying your Q node this or your Q node that, this is your Q node, right? This is your Q node. And here you have it, drawn and run. So Vardaan, do we have any questions so far?
No questions so far, although we do have comments that it's extremely easy to code, and that's amazing. The Discord channel is currently being spammed by all the entangled qubits and the images which they have received for the first ever circuit. So yeah, that's really good. One small question is regarding the output which we receive after the probabilities. The question is, in what order are these probabilities?
Oh, yeah, good question. So the qubit that you see in the top is qubit 0, and the qubit that you see in the bottom is qubit 1. I know that Qiskit does it opposite. Qiskit does it in the different order. So here you have 0, 0, 0, 1, 1, 0, 1, 1. So basically it's in the order as you see it, and it's the opposite order as Qiskit. I know that they have like qubit 0 on the bottom and so on. So yeah, great question. Something else that you will notice in the output is that it says requires grad equals true. And this is something that might be strange, but this is what this means is that if you had any parameters here, by default, they would be trainable, or the program automatically would try to find the gradients. If you do an optimization with these, the program underlying will automatically try to find the gradients. And if you don't want this, then you can add this later. I'll show you how to change this. If there is some parameter here that you don't want your circuit to find a gradient on, this is something that you can change. So great questions. I'm glad to see the circuits in the Discord. Let's now go and create a parameterized circuit. So first, we're going to create a device with only 1 qubit. So hopefully everybody in the chat, you can add your guess. How is this device going to be created? We're going to say dev equals qml.device. We are going to use default qubits. default.qubit, just to change things, to show you how easy it is to change the device. And we're going to say wires equals 1. So just 1 qubit, and we do shift enter. Now we create a parameterized circuit. And what this means, it will take at least one parameter. So we are going to add at qml.qnode. And we're going to add, oh, I'm going to call this actually dev2. I'm going to say this is dev2 so that you see the difference. It's a different device. You run shift enter again to make sure that, this is actually dev2. And now we're going to do dev circuit2, and it's going to take, I'm going to write params. So you're going to see that very often we have 2 parameters inside of a single array. And so I'm going to add 2 gates. I'm going to add qml.rx. This is an X rotation, and it will take 2 pieces of information. First, it will take an angle, and this angle will come from the first item in params. So params square brackets 0. And the second information I have to tell my gate is where to run, right? So wires equals 0. Now I'm going to do a similar thing, but with a Y rotation. So qml.ry params 1. So I'm going to extract another value from my parameters here. And I am going to say wires equals 0 again. So what this means is, spoiler, I'm going to add 2 gates to the same qubits, which is qubit number 0. And then I will perform a measurement. So the return value, which is where I add my measurement, in this case, I will measure an expectation value. So I am going to say qml.expval, and I am going to measure on a specific observable. So this is also another question that you will hear very often. I can measure on different directions. In this case, if you think of the block sphere, I'm going to measure on the z-axis. So I'm again a measure on poly-z on wire 0. This is what I'm doing here. I'm saying I'm going to measure an expectation value, and I could say I'm going to measure on the z-axis, or I could measure on the y-axis or the x-axis. In this case, I'm going to measure on the z-axis, and I am going to perform a measurement on wire number 0. Shift enter, and now let's draw it. So hopefully you all remember how to draw it. Now qml.draw_mpl. Now I'm going to add circuit 2, but instead of empty parentheses, I am going to add some value for my parameters. So let's say my parameters are going to be 0.1 and 0.2. This is some example value that could be our parameters. Let's run shift enter, and I indeed get a drawing of my circuit. So everybody, if you want to share this on the Discord, share your circuit, your second circuit that you created with PennyLane. And now you can run your circuits again by writing circuit 2, and then in parentheses you add this vector with your parameters. Let's say again 0.1 and 0.2, and I have run my circuit for these specific parameters. You can change that. You can try, let's say, a different number, and you will get a different answer. So how are we doing? Let me know, Vardaan, how we're doing in the Discord. I will go up a little bit in case somebody wants to somebody's behind.
Oh, it's going absolutely amazing. Everyone is on track. Everyone is posting the pictures of the second slide which they've created. So yeah, up till now, no doubts, no questions. Everything is wonderful.
Awesome. Great. So, you have created, your first parameterized circuit. You have used expectation values. And now we will try an optimization routine. So hopefully everybody's ready to do some optimization. We will first create a cost function. And remember, I talked to you about how do you create a cost function? My question for you is, do you add the @qml.q node? I see some no's. That's right. You don't add this because this is not a quantum circuit. This is a classical cost function. So you define it classically. Def cost. This cost function will take your parameters, right? Same as your circuit. And it will contain some classical processing. So I'm going to say the output of my cost function will be, for instance, circuit 2 of my parameters here, these ones, -1, right? This is an example of something that I could do. But this really doesn't say much. Like, I actually have no idea. I have no idea if what these values are going to be and so on, bro. I know that my output, this expectation value, would be something between -1 and 1. If it's on the negative z-axis, it will be something. And if it's on the positive axis, it will be something else. You can actually try, if you run your circuit, let's run it, for example, with 0, 0. I am on the positive z-axis. And let's say I'm going to run on np.pi and np.pi. This is maybe pi/2. Oh, maybe just one, np.pi/2 and 0, for instance. You get something closer to 0. And if you just rotate 1, you get something like -1. So don't worry too much about it. You don't have to do this. This is for me to show you. The number that you will get will be something between -1 and 1. And so writing my cost function like this really doesn't say much. So let me try something else. Let's say I'm going to take the absolute value, np.out, the absolute value of my circuit. This can tell me something. It's going to be something between 0 and 1. I can decide, actually, I want to square this, right? It's something that is you often do in a cost function. I will try to find the minimum. And so being able to have this square here will help me a lot. So let's do Shift Enter. I now have an idea of, of how my cost should look. And now we will be able to optimize it to a certain number of steps to get to the minimum value of this cost function, which again has some classical modifications to my quantum, to the output of my quantum circuit. Okay, let's choose an optimizer. I'm going to choose it from PennyLane. So I'm going to say opt equals QML dot gradient descent optimizer. I could choose a different one, but just for the example, I'm going to choose this one. And as homework for you, can try other optimizers. And I'm going to say step size equals, let's say, 0.3. This is just some number. You can try something else. And we're going to do Shift Enter. And now we can make an initial guess for my parameters. And this is where this requires grad is important. I know that I want to change my parameters to minimize the output of my function. I don't want to manually, you know, put a lot of values until I get the minimum. I want to make first an initial guess. Let's say params equals. We're again going to use, you know, the numbers that we had before, 0. Let's see, 0.1, 0.1 and 0.2. But now I am going to turn this into a NumPy array, right? So these are the initial parameters that I had before, but now I'm going to turn them into an NP array. So I put this into parentheses here. And the second thing I'm going to add into my array is say requires underscore grad equals true. Ooh, true. Okay, so I know this. I see some puzzled faces, but basically, what we're doing here is we have to give our circuit a place to start. Do you remember the landscape, the colorful landscape? We need to start somewhere. This somewhere will be 0.1 and 0.2. This is the place where we will start. And I will tell my program that this is something that I will try to modify. If I didn't want to modify this, if I wanted to say, you know, this is fixed data, I would say requires grad equals false. I could also say, you know, another option is, let me write it below. I could also say params equals np.array of 0.1 and 0.2, right? And then I could say params dot requires grad equals true if this is trainable, or false if I don't want to modify these. So basically requires grad is an information that is part of my parameters, right? This is some information that I already, basically that is assigned to my parameters. In this case, I do want to optimize, so, they are true. In this case, I do want to optimize over them, so they will be true. Okay, so everybody, I hope you're ready. Let me know. We're going to now perform the iterations. So we're going to say for it's in range of, let's say 10 iterations. We are going to get the new value of the parameters, params equals opt.step. We're going to take a step in an optimizer. We're going to do this step on the cost function, which is called cost. And we are going to start in the previous parameters, right? So my previous parameters are the initial ones, they're called params. This is going to update the value of params. And then for the next iteration, I will start in, you know, whatever this is. For every iteration, I will also print, the number of the iteration. So let's say, comma, it's, I am going to print the cost. I'm going to print the cost. And I am going to print the parameters. Okay, perfect. And if you're ready, let's see. Oops, cost. I don't want the function, sorry. I want the cost for the parameters. I want actually the answer. I want the answer of what the cost is. So cost for those specific parameters. And we get a nice answer. We start with a value that is very close to 0, but now it's 4 to the minus 5, to the minus 5, to the minus 6, minus 7, and so on. So this number gets really, really small. I noticed that we started actually at a very good point. 0.1 and 0.2 are very good numbers. We could start at something else. Let's say 1 and 2. Let's say these are our initial parameters. And now you can see, you know, at the first iteration, we get something like 0.05. And after 10 iterations, we're already at 0.003. And their parameters here have changed. They have gone from 1 and 2 to something else. Now, did everybody get the answer? Did everybody get their cost to get smaller and smaller? Let me know in the Discord.
Yes, we are receiving a lot of pictures of the correct answers. And while we are receiving them, I would like to field a couple of questions which just got lost in between all the images. These questions are from the previous examples as well. So the first question I would like to take up right now is that there's no explicit function to create measurements on the circuits. So does that mean that it is not possible to create a circuit without measurement in PennyLane?
Yeah, I mean, so if you don't need the measurement, you don't turn it into a Q node, right? So this is a very good question. Let me show you something. I can do something called, say, layer. Def layer. This is something that happens a lot in quantum machine learning. Sorry. I'm going to write something called def layer. And I'm going to add my gates here, right? I don't need to measure this. This basically will say, I will create a layer that has 2 gates, and then I can, here in my circuit, add that layer. Sorry. I can add that layer for these parameters. Now, this is not a full quantum circuit because it doesn't have a measurement, but you can add those gates to a function that you can then plug into a quantum circuit. And you can, for example, do say, let's say, for let's say layer for L in range of, let's say, 3. Say I'm going to create several layers. I can do this. This is something that I can totally do. Let's actually see how it works. See how I created, well, you know, different layers. Our XRY or XRY and our XRY. I have created several layers in a very easy way. Now, this layer is not a Q node. The Q node is circuit 2. The Q node is circuit 2, and layer is a, you know, let's say a sub part of it. It's a part of it, but the Q node itself is circuit 2. And the Q node does need a measurement.
Yeah, thank you for that. There's another question on the different devices which you took, for example. You took 2 examples of the default qubit device and the lightning qubit. So the question is, what is the difference between them, and if there are any other devices which they could try?
Yeah, absolutely. Let me show you here. Here, I'm going on the PennyLane website. On the nav bar here, you're going to see plugins. In plugins, you can see the devices that we have built into PennyLane, but also external ones that you can use. So you can use PennyLane with Amazon Bracket, with Qiskit, with Cirq, right? Some are hardware and some are simulators. But you can use them totally. You will need their own API key. So this is good to know. Yeah, you will need their own API key, but you can use them. So let's say here, I could, because I have the PennyLane Qiskit plugin installed. So to install it, you can just run, let me add something here. Wait, give me a second. So Yeah, give me a sec here. I'm going to add a new, let's say, if you want to install this locally, you would install pip install PennyLane -Qiskit. Right? This is how you install locally, or if you're on Google Colab, you would add this exclamation mark. I already have it installed, so I don't need to install it again. I can use, say, qiskit.air. And I can run my circuit. Now it, oh, here. Now it run on Qiskit Air. So this is how easy it is to change your device. As long as you have your plugin installed, you can change it with, just changing the device. So this is very, very powerful.
Perfect. Yeah, thanks for the great explanation. And the people are loving it on Discord. They are really great comments that it feels very nice to follow the lecture and try it hands-on. So yeah, on that note, please feel free to continue.
Good. We started a little bit late, but I don't know if we have some extra time, Vardaan. Yeah?
Sure.
Okay.
You maybe 5-10 minutes extra. That's fine.
Okay, perfect. So if you're ready for something more advanced, and this is an example I really love, it's to try a quantum machine learning program yourselves. We have some data. I mentioned that quantum machine learning was all about data and patterns in data. So our data is gonna be following a sine function. So we have some inputs that go from 0 to 2 pi. Our inputs are fixed. It's the places where we are going to calculate an output, and our outputs are going to follow a sine function. And we're going to use a quantum computer to be able to model find the underlying model in our data, so that our quantum computer with our circuit predicts the right output. Again, this is a toy example. This is something that will not stand any modification that you can do. This is a small example that can give you a lot of insights on quantum machine learning. So let's start by importing PennyLane, and you can use the same notebook that you have. I just have a different notebook, but you can use the same one that you have. Import PennyLane as QML, and from PennyLane, import NumPy as NP. I will also import matplotlib.pyplot as PLT. So if you don't have matplotlib installed, you may need it. If you are using Google Colab, it's already there. Step 1, I will create my data. So first, my data, which I will call X, large X, I'm going to create some equally separated data points. So I'm going to do a nice trick. I'm going to use mp.linspace. It creates, I'm going to say data points from 0 to 2 times np.pi. So from 0 to 2 pi, give me 10 data points. So this is a nice trick if you want to create some easy data. Now I'm going to tell the optimizer that X is not trainable. So X dots requires underscore grad equals false, right? This is not trainable. And now I am going to create some test data. So I'm going to say my X underscore test, because I don't want to, it's cheating if I train on something and then test on the same thing. So my test data will be slightly shifted. It will be my red dots. So my test data, I'm going to copy the same thing that I had before, np.linspace, so on, but I will shift it a little bit. I will say, let's add 0.2 and plus 0.2. So here, a little bit bigger so that you can see better. I just copied this and then shifted the data points a little bit so that it doesn't feel like cheating. Now I can create a device. I'm going to do Lightning Qubit. So I'm going to use Lightning Qubit, QML dev equals qml.device of lightning.qubits. So you open these, quotation marks because it's text. And I'm going to add wires equals 1. I'm going to need a single qubit device. And now I can create my circuit. So everybody already knows at qml.qnode of dev. And my circuit is going to be called, in this case, circuit again. My circuit will take params, but it will also take some data. Let's say, I'm going to call it, small x. I'm going to call it a small x. So notice that this is not the same x as the one I had before. This is one data point. This is small x. So I first need to embed my data into my quantum circuit. And so you notice in my presentation before, I talked about embedding data into your circuit. This is what we're going to do. I'm going to say, right in my circuit, qml.rx. I'm going to use a rotation gate to plug in my data, my training data, those points individually. So I'm going to use 1x rotation in my circuit, and I'm going to apply it on qubits 0. So wires equals 0. And now I am going to use a generalized rotation gate, so a new gate for you, qml.rot. It will take my params, and I will apply it on wires equals 0. So finally, I will return a measurement. So return qml.exp val qml.polyz parentheses 0. So the same return that we had before. So you can copy paste it if you want. qml.exp val parentheses qml.polyz parentheses 0, and close all of the parentheses. Now that I have my circuits, I can, let's say, run it for some example values. So circuits, I'm going to say, I'm going to run it for some parameters here. Notice that ROT is a generalized rotation gate, which means it takes 3 numbers, 3 angles. I'm going to say they're going to be 0.1, 0.2, and 0.3. So I create this array with all of my parameters. And my X value that I'm just going to use to test here, I'm going to use whatever. Let's say I'm going to use 0. Oh, and I get an error, which is weird. Oh yeah, sorry. I made a mistake here. Params, I need to set them individually. I told you they take 3 parameters, so I have to separate params 0. I'm going to copy this 3 times, params 0, params 1, and params 2. Basically, I need to run my circuits with all of parameters separate. It takes 2 positions. I'm sorry. I usually know how to do this perfectly, but I have my good backup here. So let me live programming is always, this is it's nice. Let me find my backup to see what I did wrong. My wires equal 0 and param 0, 1, 2. Yeah, all good. Wires equal 0 and my circuits. Oh yeah. So of course I found it. I think you're seeing my screen still. Here, I do need the brackets here. Okay, all good, all good. No panic. No panic. Perfect. So I have my parameters, which I will include here in my rotation gate. It just, my rotation requires me to pass them separately, each one individually. But here in my circuits, I have them all together. That's it. So no panic there. And finally, I can draw my circuit. So if somebody remembers, QML dot draw underscore MPL of my circuits. And right outside, I add my parameters, or I'll just copy the ones I had right before. And I get my beautiful circuit printed out. Can anybody tell me if somebody is getting there on the chat, on the Discord? I will go up a little bit, just in case you need it.
Yes, we are starting to receive images of the answers, but I'll still wait for a couple of minutes because this was a pretty long one. So yeah,
Okay.
People are still trying. Some of them are posting the images. Yes, we are getting more images.
Okay, good, good. So summary, I created some data. I said this is not trainable. I already created my test data. I created a device. I created my quantum circuit, which takes some parameters and a data point, X. My data point, I will embed it into an X rotation and my parameters into a generalized rotation, which takes 3 angles, which I will encode into my, put into my params value here. And so this is why my params contains, it's an array with 3 values. And the other one is my X. Here, the 0, it's just some random value I chose for my X. And I get my circuit. Nice. So Vardaan, let me know when we're ready to go on.
Yes, I guess we are ready. A lot of answers I'm putting, so yeah, we are ready.
Okay, good, good. We're going to add some pre/post processing. This is something that you could add at any point in your circuit. I mentioned you can do hybrid quantum programs. So we're going to call this, we're going to first do a loss function. We're going to say def loss. This loss is going to basically accumulate get the minimum squared error of all of the difference that I have between the prediction of my quantum computer, my predictions, and the actual answer. So this is going to be in training. I will get different, let's say, imaginary values of X, which will be closer or further away from my squares. And I will find, the final loss, which is the total over all of the different data points. So for my loss, I will first, and now because we don't have much time, I will, I think we have some time. Let's say I'm going to add a value Y, which is going to be my model, the model in my data, and the predictions from my circuit. And now I will compare them. So I will compare all, I will basically get the predictions. The predictions will be defined as part of my cost function, and I will compare my Y with my predictions. So I'll say my total loss starts in 0. And then for each, let's say, Y comma P in each pair in zip, for Y comma P in zip of Y comma predictions, for each pair, I'm going to add a value to this total loss. Total loss, I'm going to add plus equals Y minus P squared. So I'm getting this difference between the output and the prediction, squaring it and adding it up into the total loss. And then I will return this total underscore loss. Okay, I've got my loss function, which will add up all of these different errors. And I will create now my cost function. So my cost function is similar to the loss function, but it takes the parameters. So it will take the parameters, the same ones that I had for my circuits, and it will help me calculate the predictions. So my predictions will be the circuit running for those specific parameters. I will also say the model in my function is, let's say, the sine of x. Oh, yeah, my cost function takes my whole data as well, my whole data set, and it will calculate. So I will run, let's say L is going to be my loss. L equals loss of y comma predictions. So it basically gives us the inputs that we will then use to run my loss function. And then the output of my cost, so return, it's simply, in this case, going to be I'm going to call it C. C, which is, the output of my cost in this case. Okay, I know this is a little bit more complicated, maybe more easier for the people who already have machine learning experience, but this is just a technicality. You could have a simpler cost function like the one we did before. This is just because we have, a larger data set. Now we can choose an optimizer. This gets easier. This is similar as last time. So opt, and you can copy it if you already have, opt equals qml.gradient descent optimizer. I will say step size equals, let's say, 0.2. It can be something else. I will make an initial guess for my parameters. So params equals np.array of 0.1, 0.2, 0.3. And again, I will set them as trainable here with requires underscore grad equals true. And finally, I will iterate over a number of steps. So for it in range of, let's say, 10. My parameters, actually, in this case, because my cost function includes parameters and data, then this will output it together as one. Params and x equals opt.step. It will take my cost function and it will take everything that my cost function takes. So parameters and x. Now, because the parameters value needs to be updated, I will simply extract it from the output here. It will be the first one because it's the first one in the cost function. It's also the first one here and the first one here. So the first value here will be the new value of my parameters. And I will now print the iteration. Print the iteration, and I will print the cost, which is simply the cost for those. I'm sorry, here I made a mistake. The new value of params equals params and x here. So the cost for the new value of the params and also x, which are the two values here in that my cost function, the two arguments that my cost function takes. I will add them here, and that's it. of course, I get an error because okay, of course here. My circuits also takes a specific, oh yeah, of course. My circuit only takes a specific X, not the entire data set. It only takes a specific X. So I missed a step here. So for X in, yeah, so yeah, let me make this easier here. For X in X here. So I have these squared brackets that help me make an easy for loop. This is just an easy for loop for each individual data point in my entire data set. For each individual data point in my entire data set, run the circuits for those parameters and that data point. And all together, this will become just an array with all of this data. And so now I get an output. Now 10 iterations is very little. 10 iterations is very little. So we can, try to run it for more iterations and get a different value, right? In this case, maybe the step size was, it may be not right. Maybe you started at a bad data point, but you can try different ones. So we can change the step size, say, to 0.1. These are some things that you sometimes have to try, and this is better. Step size of 0.1, and I get much smaller values. They're really conversion to something small. If I wanted, I could, print the parameters, the last ones. I could print the last value of the parameters here. So these are the last value of the parameters, which are not the same ones that we started with. These are different. And I know that I'm cheating here. I already had some plotting information. This is simply for plotting. So only for getting a nice graph. I can, I think I call this X, large X. I know, I call this differently, but basically you can just make a nice plot if you want. So I think, here the order is different. I simply added my parameters first. All right, all good. You see that this is really done in real time. I first get each individual data point in my test data. I run my circuit with the final parameters. So these are no longer being iterated over. These are the final parameters. I run them in my circuits together with each individual data point. And this gives me the test prediction. So these are the X that I have in my QML. And now all I do is I create a scatter plot where I am plotting my original data with the original output, which is sine function, my test data with the output, which is again a sine function, as well as the X test, which is, the X points, as well as the predictions for those X tests. I label everything and I get a nice plot showing you that this very, very simple circuit actually indeed managed to understand the underlying model in the data. So I know this was complex and, we went a little bit over time. I hope you got a sense of also, basically how a quantum machine learning program works in general. It has a lot of different steps, but it's not too complicated once you get used to it. You just need data, you need a device, you need a quantum circuit, and you need to define your cost function. If you want to, test for all data once, you can define a loss function. There are different functionalities in PennyLane that, allow you to run batches, so make this easier as well. So this is just one way of doing things. but you can do it differently, and you can make it more optimized. This one was just to show you the details of, how you would do one quantum machine learning program, optimizing it, from 0 to 100 to everything. So hopefully, whether this was easy or confusing, you will want to learn more. I want to give you some next steps. If you want to keep improving your skills, we have some really excellent learning resources. The codebook, Xanadu codebook, and the Xanadu YouTube are great. We have new content coming up, so definitely stay tuned. Also look at the PennyLane demos. So I showed you the PennyLane website briefly. It has excellent, really, they're very known in the field. These are more advanced. We have a lot of them on quantum machine learning, such as a variational classifier, for example. This is one you can try. And if you're interested in going all the way up to research, we also have it on the Xanadu website. Now, if you're interested in careers, our residency program, which is our main internship program, the applications will open around September to November for coming to Toronto in May to August of next year. Or if you are interested in working full-time for us, definitely look at our careers page. And please join the community. We have a lot of people all the time being very open and willing to help you. We have, so many users, so many people that, come from all different kinds of backgrounds. It's a very diverse and open community. So definitely join us, whether it's asking a question on our forum, discuss.pennylane.ai, contributing to open source. It's a great way of getting your, your resume, your skills up, or talking on Slack. So you can also join the newsletter. This will give you a summary every month, once a month, of everything that is going on, and follow us on social media for more. So I hope you enjoyed it. I know that we went over time, but hopefully you'll all get to enjoy everything that we talked about today. And I look forward to next time.
Wonderful. Thanks a lot for that great demo. The participants really enjoyed that. They have huge comments coming in that it was a great session. It was really hands-on, and we loved everything that we experienced step by step. So yeah, thanks a lot for that. One quick question is that, is it possible for you to share the notebook which you used in the demo? Yeah,
totally. I can share it. It is better to not know it before, right? Because otherwise you don't get into into the excitement. But yes, I will share them with you, Vardaan, so that everybody can have them.
Absolutely. Yeah, so that's great then. Just share it to us, and we'll share it further with the participants as well, so that in case someone missed out on a certain code block or something, they can always refer to it.
Okay, perfect. Thank you. Thank you very much for the invitation, everybody, for the excitement, for the comments. And I look forward to hear more from you on the discussion forum or on the Slack as well. So let us know that it came from here. And yeah, I'm excited to get all of you into the community.
Absolutely. And Xanadu has been a huge part of our quantum program. This was an amazing session. But stay tuned. Next week, we are also holding a Quantum Solutions Launchpad Spotlight, where Xanadu will be again here, and they would be talking about how they are participating and collaborating with us on the Quantum Solutions Launchpad. So again, there's a great chance for you to learn more about that.
And then on Friday at the career fair, where you will hear more about all opportunities at Xanadu too. Amazing. Thank you so much, Catalina. Great workshop.
Yeah, hope you enjoyed it, and I hope you enjoyed the notebooks as well. Have a good day, everyone.
Then a brief overview of what is coming up tomorrow. Tomorrow, CQTech will offer a virtual office hour for questions about QNickle and tutorials on QNickle. You have until Sunday night, American time. So yeah, Sunday night basically and beyond for everyone to finish QNickle. So this is one of the last good opportunities to ask all your questions about it. Then tomorrow we will have a hardware lecture and virtual lab tour and software tutorial on quantum annealing hosted by D-Wave. This will be a really good session, so definitely be there. It is a very different technique than all the gate-based or mostly gate-based techniques that we worked on so far. So definitely join. And then the second half of tomorrow's session will be the career training, where we will focus on how to give the best 15-second pitch of yourself to the recruiters at the career fair and how to write the best resume. That was it from my side for now. Fun, exciting session today. Thanks so much for all involvement on the Discord. It was really great. And we have further team members here, Raj, Haisa, Vardaan, to answer any other questions, to share more about the Global Quantum projects, to share more about the Share Your World. Oh, let me point out one more thing, which is very important. I will return to screen share. From tomorrow, after the career fair training, you can upload your polished and improved resume on Canvas. This will be a separate assignment. I will briefly show it to you, so it is all clear. We have now the assignment career fair, and right now the instructions are shared there. Tomorrow also the resume upload will open, and here the prerequisites are also outlined. What are the 3 steps to participate in the career fair? Most important, upload a really good polished resume by Sunday on Canvas. Format, PDF, file name, last name, first name, resume. Then we will give priority to the people who are advanced with all the modules that we are offering. So make sure to complete either module 1, QNICL, or module 2, QKD, by Sunday. And also make sure to make at least a start with module 4 and 5 and get at least 30 points in both. Then on Thursday, tomorrow, we will offer the career fair training. Please be there. And if you don't make it, watch this YouTube recording where also pitching and resumes are being discussed. Yes, I will stop sharing. Let's see if there are questions on Discord, and the team will be there to answer.